All right, welcome to 2P04 test number 10 prep. So this is going to be our flexural elasticity test here, and we're going to look at test number 9 from 2016 first, and then we're going to look at an exam question from that year to get at the piezoelectric stuff. So first, questions 1 and 2 here deal with a lot of the shear force and bending moment deflections. So this is just going to be dealing with not any thermal expansion or piezoelectric things, just shear force and bending moment. So this first question says a solid aluminum cantilever has these dimensions and is fixed at the left end when this mass is hung off of the right end. Consider the aluminum density is that. So considering that's the aluminum density, figure out the deformation of the tip from bending deformation alone, shear deformation alone, bending and shear via superposition, and then bending and shear via flex PDE. So this is going to be the first ones we're going to be using maple to figure this out, and then we can figure it out with flex in this last situation there. Okay, so what we're going to need to do is start off with a free body diagram, and just to build this, we've got let's put a wall there, and then let's go and grab a rectangle to show the beam. Okay, so this is going to be the aluminum, and aluminum is sort of this like whitish gray color. Maybe we'll give like an outline, or guess we can fill both things in there. Yeah, that looks like some aluminum. It's a little bit darker than it's supposed to be, but I guess we'll deal with it. Okay, anyway, we then have we're gonna draw the forces on this to make it a free body diagram. So let's go back to this setup here, and maybe we'll draw the forces. You can right click to select the color I just figured out for the secondary, and we will draw a force at the end. So this would be the 20 kilogram weight. So this is maybe W at the tip, and then we've got another distributed load all the way throughout this thing, which is from the mass of the aluminum. So maybe to do this, what we'll do is draw that as just like a distributed load at the top of it. It's not really, right? It's actually a distributed load all the way throughout. So let's just draw this thing, a couple of arrows throughout here, and we'll call this W at X, and that's just going to be a constant. So that's our distributed load down from the weight, and then we're going to have some reaction forces at the wall. So at the wall, we've got maybe this RY for reaction in the Y direction. There's nothing in the X going on, so then we can jump right away to the moment, and let's just draw that in that direction. M at the wonder what to call this. Maybe MW for M wall. Yeah, all right, that's good. So here's our free body diagram. And now we can jump back over to our notes here, paste that in, and then we're ready to go and calculate what the internal shear force and bending moment is. So the point of the internal shear force and bending moment is so that at any point you say, hang on a sec, you know, this thing has to be in equilibrium on each side. So that means that we must have some internal force set up. So maybe we'll take red here and use that for the internal shear force. And our regular sign convention for the shear force, I believe, is that V points like that, and then it's equal and opposite on the other side. So this is representing the force that this right side must be putting on the left, and the Newton's third law pair, which is the force that the left side of this beam must be putting on the right at any junction. So V is going to be a function of X, of where along this beam we are. Maybe we should draw that. We should draw what our X axis is. So this is X, and then we've got Y in that vertical direction. Okay, so the other thing we're going to have is a bending moment applied on this center face, and the default sign convention for that, I believe, is that the bending moment is going around like that. And over here, equal and opposite bending moment would be that way. So we can label these M, and M is for the internal bending moment. So if we copy this and then paste it into this document here, then it gets rid of those checkerboard things on the background. So that's gone. So now we're all good. So this is a good diagram to use to draw the internal shear force and bending moment. And we can use this now to figure out what those are. So now we're jumping over to any computer algebra system that you like. I'm going to use an older version of Maple here, but you can feel free to use whatever you like. Then looking at the left side of this, we can write out the net force in the y direction, and the net moment about any point, maybe about the wall there, is equal to 0. So first we're going to maybe sub in the parameters that we got from the question. And the aluminum was 2700, and the M tip maybe is equal to 20. And we're going to need G is 9.81. So we've got W tip is equal to G times M tip. And we'll need the mass per unit length and the weight per unit length. So what this weight kind of distributed bending, what this distributed load is. And for that, we're going to need the dimensions of this. So it's 1 by 0.1 by 0.1. So we've got L is equal to 1. Maybe the cross-sectional, let's say B is the width into the page, and that's 0.1, and H is equal to 0.1 as well. That's the height. That's the kind of the length in Y. Okay, so that means the cross-sectional area is B times H, and the distributed load is actually a constant. It doesn't depend on how far along we are in X. This is supposed to be the force per unit length X. So we can get the weight per unit volume, which is density, and then multiply that by G, and that would be the mass per unit volume is rho. Multiplying by G is what gives you the weight per unit volume, rho G. Now we're going to multiply that by the cross-sectional area, and if it was per unit volume, we've multiplied by area, now it's per unit length. If you were to then multiply this by the entire length, you'd have the total weight. So as it is, it's the weight per unit length. Okay, that's not the only way to do it. You could look at the effect that this should have on the, that this distributed load should have. It should be the same as the total weight, just applied at the center as far as what it creates in terms of reactions, but it's not going to be the same for the internal shear force stuff. So we better keep it all spread out while we're looking for what that internal shear force and bending moment is. Okay, so there's W. Now, once we have that, we can say what the reaction at the wall is. So we have Ry. Maybe we'll use a solve just like we used to here. So we're going to solve Ry minus the integral of W, x is 0 to L, minus W tip is equal to 0. And we're going to solve, let's add the moments in the, let's say, counterclockwise direction. So we got MW minus the integral of W times x is 0 to L, minus W tip times L. So there we go. That should be telling us what the reaction force at the wall is and what the bending moment is. Now, just as a check, we should have found the same thing if we had just used the total weight of the beam down and the weight at the tip. So let's say W tip plus rho times L times AC times G. That should be also equal to the reaction force at the wall. Yep. And if you wanted to know the moment, you could say W tip times L. And then for this one, that's kind of averaged at the center of mass, which is halfway down the beam. So that should also give you the same moment. Let's see. Yeah. So everything works out. Check. Seems like it's correct. And we've successfully solved for the wall's reaction force. Next thing we need to do is figure out what the shear force would be in this setup. So looking at just this left diagram here, we can solve for what the internal shear force would have to be by doing the same kind of a setup, just remembering that this depends on x. So from this solve, we will assign this. So now we've got those, that ry actually assigned to those variables. So we're all good. And then we can take a net force in the vertical direction is 0 and net moment about, let's say, the left end is equal to 0. And if we do that, then we're going to have that let's see. So we would have solve ry minus the int of w from x is 0 to x minus v is equal to 0. And we would have for the moment one mw minus the integral of w times x is 0 to x, minus v times x, plus m is equal to 0. So because we don't have any piecewise, this should actually work. Remember that if you have piecewise functions, then what you have to do is go and mess with this a little bit and rearrange, and then just say, okay, you can use this system to write out the equation so it's easier, and then you can just solve this for v by bringing v right over to the other side, and solve for m by bringing that over to the other side. So let's assign that, and then as a check, the moment that we have should be equal to what we would have gotten if we had just integrated the shear force. So integral of v with respect to x, and then we're going to go minus mw and see what we have there. And it looks like we are all exactly the same there. So one thing is that we got a little bit lucky with this thing, because we actually didn't tell it what to solve for everything in terms of. So it's possible from this set of equations here, where we have really three unknowns, v, m, and x, that Maple would have just said, okay, let's just solve it for m and x in terms of v. So we'd better tell it to solve for v and m, and that just guarantees that it'll do exactly what we said here, so that it solves for everything in terms of that x. Okay, so now that that's done, we can check that everything works out by plotting v and m for x equals 0 to L, and see if the setup makes sense. So the moment starts at the moment that we had applied at the wall, and it rises up towards 0 because we don't have any moment applied at the tip. The internal shear force that the right side is putting on the left starts at enough to balance out ry, and then decays down until it is equal to the force that just that weight at the tip is applying to the rest of the beam. So that works out. Now this is the same as we would have gotten if we were looking at the other side. So you could say, all right, well, at the right hand side, the force up that the left part of the beam must be putting on this thing must counteract the force of the tip, of the tip weight there, and then it has to rise up more as it's supporting more and more weight of the aluminum until we get over to the left, where it is the same as the force that the wall is putting on this beam. Now, for the moment, the bending moment is actually starting at 0 because there's no applied pure moment at the end, and then the moment in this direction gets negative because we are already trying to spin this thing in the same direction that this moment would make it spin. So we have to apply the opposite moment as what's shown there to stop it from twisting, stop it from spinning about some point. And then that just gets to a larger and larger negative value until we go over to the left and it equals the moment applied at the wall. Okay, so all of that is to some extent kind of like old news, right? So this is all stuff that we would have been able to do before. The new stuff in this section is that we can figure out what the deformation should be, not just from the shear deformation, but also from the bending. And the reason we didn't look at these plots where we have a shear force and a bending moment and calculate what the deformation was from just the shear force previously is because, as we'll see, the majority of the deformation is actually from this bending moment. So, a couple of things. Bending deformation alone is calculated through a series of things that go through the curvature. So if we jump over to the lecture notes here, then you can see the basic setup of this right at the beginning of the beam bending thing. And then essentially what they're getting at is this derivation that we've ended up with with how the bending moment relates to curvature. So curvature, which is 1 over the radius of curvature, is equal to the moment that's applied in the direction shown, divided by the flexural rigidity for bending about this axis, and that's based on how far away points are from the center, from the centroid of that axis about that given cross section. Right. So basically, this integral, this second moment of area, is based on a given cross section here. The y direction would be up, so we're integrating over the shape of that cross section to figure out what I is, and the location of the centroid is where the y coordinate is for the average over that area. Now we can calculate this for the rectangular beam. Yeah, so the rectangular beam that we have has a, let's just suppress the plot for now. The rectangular beam has a cross section which is located at the center by symmetry. But let's suppose that we don't know that, and we're going to figure out where y bar is. So y bar would be equal to the integral of y over the area. So to integrate over the area, we would just multiply that by the width of the beam, and then integrate from y is 0 to h. So this is if we're setting the y equals 0 spot at the bottom of the beam. And then we're going to divide by the same integral over the area of just the number 1. So this should be the total area of the beam, which should be b times h. Yeah? So if we take this, what we're going to find is h over 2. Yeah? So because h is 0.1, then what we did find is h over 2. If we had not actually assigned an h before doing this, or if you integrated from 0 to like capital H or something so that we'd have an unassigned value, then you'll see that this is always going to be the case, right? So you'll find halfway up is the location of the average. Then what we can do is we can say that I, because I is a reserved thing in Maple, I got to call this I2, would be equal to the integral of y minus y bar squared with respect to area. So this is times b, and because there's no change in that in the width direction, so we can just multiply that by the width, and then change the show the integration variable going from y is 0 to h. So this is over the whole thing, and what we should find is that we get b times h cubed over 12. So we'll just compare to that, b h cubed over 12, and we'll have the same answer for these things. Okay, so that's the second moment of area. This goes into its resistance to bending. That's the geometry effect on resistance to bending. So you can use this to figure out what the total curvature of the thing would be. Okay. So really, we should end up, to make this the most general as possible and account for a stiffness that can change with position in the vertical direction, we should end up multiplying this by the stiffness in the extending direction. So what I mean is account for the way that the stiffness in the lengthening direction, because that's the kind of deformation that we've got. As we twist this, it's compressing in the length direction and extending in the length direction. So that's like the x direction I'm talking about here. But if that stiffness in the x direction changes in the y direction, we should really put this into the calculation of y bar here. So we should average that y, weighting it by the area times the stiffness. That's really what y bar is, right? This is an average y weighted by the area. And really, if you have this change in E across the beam, then you should do the AE weighted centroid for y bar, and to treat E times I as a single thing that you're finding. So that's the flexural rigidity. This is accounting for multiple beams in this flexural rigidity definition section. So using the more general one, we can put E inside. I mean, in this case, it's just a constant, so it's going to cancel in that integral. And then we'll find EI by integrating E times this y minus y bar squared over the area. It's kind of nice to just stick with finding EI all the time in Maple, since while I is a reserved thing, you can do EI as a regular variable. So the only difference is in finding y bar, you account for the fact that E could possibly be changing with position there, and then you put it into your flexural rigidity calculation as well. So there we go. We've got our flexural rigidity. With the flexural rigidity, we can figure out how the what curvature we're going to be getting by using the formula right at the beginning of the section, and that is the fact that the curvature is moment divided by EI. So at any point in this beam, the curvature is the moment divided by EI, and there we go. So EI is just a material parameter. It doesn't change. So material / geometry parameter for the beam. So the curvature that we have is changing with position, proportional to the moment, and this curvature leads to a deflection in the beam, at least for small deflections that we can calculate using this relatively simple formula, that the curvature is the second derivative of the vertical displacement. So really the beam forms into this circular arc, yeah? And so we should use some a little bit more complicated geometry to find out what the displacement of that would be. But as long as the square of the vertical displacement is much less than 2 times the vertical displacement times the radius of curvature that we've got, then we're going to have a situation where you can say that the vertical displacement is basically c times x squared over 2. After, well, okay, hold on. This is only if the curvature is actually a constant, right? If the curvature is changing, then all the way along for a very small step into the next spot in the beam, we'd better use the fact that curvature is the second derivative of the vertical displacement, and then just double integrate that, and that's going to account for the fact that curvature could be changing with position. So what that means is we're going to say that v is equal to the integral of c from x is 0 to x is 0 to x, and see what we get. So we've got 2 integrals of c, and this is going to be the v, really the v from bending. Okay, so that's the vertical displacement we got from bending. Now the question actually asks us to figure out what the deformation from bending is at the tip of the beam. So to do that, we just substitute in the length of the beam for the x position there. Okay, so v bending tip is equal to subs x equals L into v bending, and we find that it is 0.00017, so 0.00017 meters, or about 167 microns. So not very much, and it says it's negative, which is consistent with the load that we're putting on this thing. So the vertical displacement is down. All right, so the sign convention seems to be holding strong. Okay, next one, shear deformation alone. So for shear deformation, what we're going to do is use the fact that the shear force is related to the shear strain. So by the shear force gives you the shear stress after you divide that by the cross-sectional area. So that's the shear stress. And specifically the shear force that we've assigned in this picture. This is the, if we're looking at this this V inside here, what is this? This is on the X face in the Y direction, kind of, right? Because V, as it's assigned going down here, is really the shear force on the X face in the negative Y direction. So that would really be negative tau XY, yeah? And then the shear force on the X face in the Y direction is supposed to be equal to the shear modulus times the shear, where's that symbol? There it is. Oh, of course. So the shear strain on the X face in the Y direction. And that would be specifically the displacement, right? So this is the displacement per step in the X direction, the displacement in the Y direction. So the change in the Y displacement per step in the X direction using our typical symbols that we're using for these things. Okay, so then what we need to do is say that is basically solve this for how V depends on the shear force. So what we get is that V is equal to the integral of negative V over AC times the shear modulus dx from 0 to x. Okay, and this would be the displacement just from the shear force. Cool. So with that theory behind us, we can go and calculate it. So let's say V, I guess we're going to need G, right? G is E over 2 times 1 plus nu for an isotropic material. And then we've got V shear, maybe sticking with camel case to be consistent with that. V shear would be equal to negative the integral of V over AC times G from x is 0 to x, and V shear tip would be equal to what we get when we substitute x is L into V shear. And what we expect is that this is a lot lower than the bending deformation. So we find V shear at the tip is only 1.27 microns instead of 168 microns. So the shear force, if you look at the at how it's depending on x for this whole thing, the bending force seems like it's based on these constants that go like x to the 4 at the tip, and the shear force goes like x squared. So it looks like shear force is based on 2 less powers of x than the bending force, but it might be a little bit more complicated than that because there's other things going on with the with where the weight is applied, how the weight of the beam is calculated, all that stuff. So that is the calculation for the shear force at the tip. To figure out what the total is from superposition, that just means acknowledging, hey, wait a minute, these are both linear phenomena. So the total bending, maybe V tip would be equal to V shear tip plus V bending tip. Okay, and in total, it's basically the same as just the bending one. So we can ignore the shear deformation and not be too far off for a beam with this kind of aspect ratio. So the last part of this test asks us to figure out what the bending and shear deformation is via FlexPDE. So for this, we've got this FlexPDE script from a couple of videos ago that's doing some crazy stuff right now. And this was the start of the general elasticity video. So we're going to go back and modify this to be an isotropic material. If you have one saved for an isotropic material, then you can just use that. I'm going to start with this one just because it seemed, I looked for it for a bit and it was taking me longer to find an isotropic save file than it would be to just go and redo it. So what we will do is go back to the notes and go into the first part of Voigt notation. And there's an example here where we point out what the matrix looks like for an isotropic material. So that's this. This is our stiffness matrix for an isotropic material, and that's exactly what we need. So we're going to take E over 1 plus nu times 1 minus 2 nu times 1 minus nu, and then the same thing times nu for the off-axis component. So that first one is for the diagonal, and then the off-axis components, and then the ones over here are just the shear modulus. So that's a little bit easy. Okay, so going back to Flex there, we're going to calculate C11 is exactly that thing. So let's move this over there, and maybe let's go to make the font a bit smaller, like maybe a size 8, just so that you guys can see it a bit easier in the video. Great. All right, so we will say C11 is E over 1 plus nu times 1 minus 2 times nu. Then we're going to take that thing and multiply by 1 minus nu. And C12 is equal to the same thing, but multiplied by nu instead. Now we need to change what the nu and the elastic constant are before I forget about this. So let's go back to the test here and see what we had. We had 70 gigapascals, 0.35, and there we go. Okay, so this is I subbed this into the wrong spot. So that should actually be C12, the diagonal component here. So this is C11, and this one here, C33, is also C11. And then here, the off-axis are all the same. And these ones are all 0, so we don't need to say 0E9. Let's just say 0. And we are going to have, for C44, we're going to have G. And then same thing here. C44, that's just 0. And yeah, so there we go. Isotropic material, we are all good. The comment now makes sense. Good thing we never deleted that when we messed around with it later, and it became non-isotropic. So we're good to go. Comment has become useful again. All right, perfect. So yeah, so far we've just kind of gone backwards in time with FlexPDE and turned it into an isotropic material. Now you might be wondering what we have to do to get this load accounted for and deal with the bending deformation, and the answer is nothing. Actually, FlexPDE has been doing this the whole time. So all you have to do is put in a load at the tip in the y direction that's going to be related to the weight after you multiply it by the area of the tip here. So the load at the tip would be the weight of the tip, which is 20 times 9.81. Now to put that into the stress that we should have there, you're going to divide that by Ly times Lz. So divide by the area of that face. Okay, perfect. Now there's a few different ways to account for the distributed load over the top. You could, on the, let's anchor it at the left here, and I'll finish that thought in a moment. You could over, man, I seem to be typing los a lot today. All right, so you could over the top surface, the y equals Ly surface. This is the top in our setup here. You could over that thing write a load in the negative y direction, which is equal to the total weight of the beam distributed over that surface. So that would be the density times the 9.81 multiplied by the volume, Lx, Ly, Lz, and then divide that by the area of the top, which would be Lx times Lz, right? So this is one way to do it. And so, I mean, you can see by how this works out that turns out to be the same as taking the total load and then the weight per unit length, weight per unit volume, and then multiplying it by Ly, because then you're going to be integrating this load over that top surface, which has an area of Lx, Lz, in order to get the actual force that's applied to that surface when you do this. Okay, so that should work. If we put in the density above, we should get something that's pretty close for the answer we were expecting. Rho is equal to 2700, and we got to put in our dimensions, 0.1, 0.1, and let's see what we get. Okay, lots of funky pictures here. Magnification, we can't see anything. There's too many things in the summary table for it to report it accurately. Too many plots here. But what we were looking for is what the value in the of y displacement is, and we have 168 E minus 4. which actually is closer to the calculation of just the bending deformation than it was to the total of the two put together. So that seems like it's pretty good. Now we applied the force uniformly over the top. So rather than doing that, another thing that you could do is apply the force throughout the volume. So how would you do that? Well, in the v direction here, you would say this is the net force on the cube from the stress parts. You would also just add in the force from gravity. So that's minus rho times g, right? So this is supposed to be a force per unit volume. So we've also added over a force per unit volume here. And so we should get the same answer if we do it this way. It looks like not. Something has gone seriously wrong there. So what happened differently? Oh, aha, I figured. Did you see it? So G is not 9.81, right? G is the shear modulus. Okay, so that's quite a lot more gravity than we were expecting. And just because, remember, Flex PDE is not case sensitive, putting that small letter is going to seriously mess things up. So hopefully by seeing that, you guys will not make the same mistake. Okay, so we have something which actually still doesn't look like it agrees, right? So we've got 6.7116 E minus 8. So that's no good. There's something else that's amiss here. Oh, I found it. So the problem was I zeroed out the wrong force, right? So I left the force on the top here and removed the force at the tip, which is still there. So we're supposed to leave this one in and then replace the weight of the beam itself with this distributed load throughout the center. Okay, so now we're all good. And we still have a mistake. Okay, I found this one too. So we're in the load here in the tip, at the tip should be in the down direction. So the two things were competing with each other. Okay, so all right, finally we have the displacement in the correct direction. So it's negative 1.68. It's I think the other one was wrong before when we were doing this. So this one really, we should have said that this load is in order for it to balance what we had earlier. So if we want to just say that this is equal to 0, then we would end up with negative 1.68. So that's what makes the sign work out in this setup. So we've got that displacement at the tip. Now this is really the displacement at the top of the tip, not at the center. We can work that out by saying, just giving a different setup here. So we've got V at Lx, Ly over 2, and del Z over 2. Let's see how different it is right in the middle. At that point, it's only slightly different. So pretty much the same thing, but not quite the same. We can increase the N grid for this setup. It's possible we can go up to 15 with this aspect ratio. Let's see. Yeah, it looks like the student version makes it. Okay, so we've got negative 1.68 E minus 4, or 168 microns. Cool. Okay, so the last thing that this one asks us about is to repeat that question, but assume that the beam is 0.1 meters rather than 1 meter long, and then comment on how important shear and flexure deformation are in question 1 versus this question 2, and explain why. Okay, so if we change things up here in Maple, this is one of the beauties of having done this whole thing with a computer. All you got to do is change this to 0.1, and then you can completely recalculate everything. So we've got now that bending gives us a displacement of 0.1 microns, and shear is almost the same actually, 0.08 microns. So the total thing is now about 50-50 bending and shear. Let's have a look at what Flex says. So if we kick this back down to a grid of 5 so that it'll run when we're in the cube geometry, change X to 0.1 there, and then redo this calculation, we've got a bending on the tip that agrees. It's about 0.2 microns. So now we're pretty close again to the flex deformation, but not exactly the same. So maybe about 4% off from what we calculated with flex versus maple. And this is giving us an idea about what's going on with the shear importance. So you see the shear is about equally as important as bending moment when we have a cube type shape. But if you move to a longer beam, then the moment becomes quite a lot more important than the shear. So that's the reason for that. The moment, both the bending moment deformation depends on the bending moment that's applied. And this gets stronger for a given shear force if the beam is longer. So it scales with the length of the beam times that force that's at the end. And so the numerator goes up by a factor of length at least, and the denominator here, whereas the shear force, it's just sort of the same, right? It doesn't necessarily get bigger if the beam's longer for a weight applied at the end anyway. The flexural rigidity changes so that this is inversely proportional to the square of the displacement, and then you integrate over the area. So so after you integrate this thing over the area, it goes like it scales dependent on the thickness importance. So the relationship between, I mean, this thing doesn't change if the beam just gets longer, but its relative importance does change because it goes like the thickness cubed. So for a given curvature, even if EI is holding the same, moment has gone up by a factor of length, you've got the curvature going up by a factor of length, and then you integrate this twice to get the displacement from that curvature. So that means that you go up by a factor of 2 more lengths, whereas for shear deformation, you'd only be scaling it with a factor of length because you just integrate once to make that shear deformation calculation from the shear force. So moment is going to be scaling kind of like x cubed for a given fixed shear force, whereas shear deformation is going to scale only like x. That means as you make the beam 10 times longer, the moment deformation at the tip will go up by a factor of 10 cubed, like a factor of 1,000, whereas the shear will only go up by a factor of 10. And that's kind of what we saw, right? So the shear deformation is now 0.1 microns, whereas before it was on the order of 1 micron, and the moment is now 0.1 microns, whereas before it was 0.1 millimeters. This video is getting kind of long at this point, so I think for part 2, for the internal strain deformation, we're going to pick this up in a separate video. So watch out for that coming out soon. Thanks for watching. I'll see you soon.